So everyone likes to see how this theorem can be applied to a practical circuit. I've got the theorem summarized up here, and here's the circuit we're going to apply it to. It's a fairly simple one. We've got a current source that's got an easily broken down Fourier series equivalent. You can just read out the components from the way it's created. It's got a DC value. It's got something that's fundamental, which is 1 radian per second, and then a certain amount at its third harmonic. One capacitor, one resistor, and the question is find the average power absorbed by that resistor. So we start off with saying what Parseval's theorem says in words, that the average power dissipated by that resistor is equal to the power dissipated by that resistor at DC plus the power dissipated by it at the first frequency plus the power dissipated by it at the second frequency, and so on and so on. And for this circuit, that's going to be the DC component will be the voltage across and the current through that resistor at the DC value plus, according to this equation, the sum of 1/2 times all of the powers contributed to it at each of its harmonics. And that's a multiplication symbol. Let's see. That'll be the phase of its voltage minus the phase of its current at its nth harmonic. So that's it. So let's do it first for this. Let's compute first its DC component, and then we've only got two AC components, one at its fundamental and one at its third harmonic. So let's start with that. First, we're going to do it at the DC component, at the DC frequency. So the DC component of all this is just a 2 amp current source, and at DC that capacitor becomes an infinite impedance, so we've got a 10 ohm resistor. And therefore, since the voltage across it at DC is, by Ohm's law, 2 amps times 10, which is 20 volts, and the current has to be 2 amps set by the current source, so that gives us together that the power at DC frequency, at 0 frequency, is equal to 40 watts. Next, at the first frequency, at omega equals 1 radian per second, we've got I'm going to draw it in the frequency domain, so we've got a phasor input, 10 amps, the phase offset of 10 degrees. Our capacitor looks like a 1 over j omega c. So over in this little scratched area, I'll just check out that 1 over j, our omega is going to be 1. Our capacitance is 2, so that gives us 1 over j2. So that is equal to 1 over j2, and we know that 1 over j2 is the same thing as saying minus j 1/2, since we already know that 1 over j, if you multiply it by j over j, we know j over j is 1, so we're not changing the 1 over j. That would be equal to j over j squared, which is the same thing as j over minus 1, which is the same thing as minus j. So we can rewrite this, therefore, as minus j over 2. Our resistor doesn't change. It's still 10 ohms. And we want to find both the voltage phasor across it, and we want to find that current phasor through it. I'm going to call that I sub 1 and V sub 1, since that's our first component. So let's see, V sub 1. How can we figure out what V sub 1 is? I suppose we could do a mesh. We'd have 2 meshes. Well, we know what this mesh is, so we just have one mesh. That would work. Of course, that would give us I as a result, and we're really looking for V. We could do a nodal. We'd have, put ground down below. We'd have one equation, one unknown. I think it's even easier, though, to say that the voltage across this element is the same as the voltage across both elements. So to find that voltage, we can find its equivalent impedance of that capacitor in series with that resistance, and we're not going to change the voltage across it. We'll definitely change the current through it, but we can find that V1 just by putting these two guys in parallel. So in other words, we're going to put the parallel resistance, the parallel impedance of that minus J over 2 capacitor with our 10 ohm resistor. And that's going to be equal to, I'm going to skip the algebra. I'm going to assume that you feel comfortable with that. No, you know, on second thought, I will do that. That's product over sum, so that's going to be minus J5 over, and it's going to be kind of ugly, isn't it? 10 minus J over 2. I think I probably, before I put that in my calculator, probably multiply top and bottom by 2 maybe, make it a little bit nicer. 20 minus J, that's a little bit nicer. All right, so we got this. So now we can say that this voltage is going to be equal to our current source, 10 at an angle of 10, times, by Ohm's law, the equivalent impedance of these two guys in parallel, which we said is equal to minus J10 over 20 minus J. That gives us 5 at an angle of minus 77.1. So nice to have your calculator do the heavy work. Now to find that current, we said we can't do the same thing for the current. The current is going to, we can't combine these things or we'll destroy the current. So one way to do that, the simplest way, the way I don't want you to do it, is with a current divider. You could say that the current through here is equal to this current times this over the sum of the two, and that would be correct. But it's a whole lot easier saying, hey, if I know the voltage across the 10 ohm resistor is equal to 5 at an angle of minus 77.1, and if I know that that resistance is 10 ohms, then just divide the two to get current. And so just by inspection, the magnitudes divide. So 5 over 10 is a half. And then the angle is the angle of the top minus the angle of the bottom. And since the angle of the bottom is 0, by inspection that gives us this. Now when we multiply them together, we can say that the power, therefore, at the first harmonic is equal to 1/2 times 5, our first thing, times 0.5, our second thing, times cosine of the difference in the angle. But since we could literally write minus 77.1 minus negative 77.1, and we would have to write down the angles if it was if we're asking to find the average power dissipated by something other than a pure resistor. But for a pure resistor, whatever these angles are, it's going to be the same. So the difference of the angles will be 0. So that means that this is just 1, and we end up with 1/2 of 5 times 0.5, and so that gives us 1 1/4. Let's do the same thing for the next harmonic. Now the next harmonic, there is no harmonic. The second harmonic is 0, so the next one we're going to do is going to be at 3. And at 3, at the third harmonic, we now see that there is a 6 at an angle of 55 component through that current source. And you know that that capacitor is no longer going to look like a minus J over 2 impedance element, that the impedance changes with frequency. It still looks like a 1 over J omega C, But now our omega is no longer 1, but now our omega is equal to 3. And so when you plug in the 1 over j 3 times 2, it's 1 over j6. And our resistor stays the same. We still want to find the current through it. We still want to find the voltage across it. We can use the exact same methods we did up here to say V sub 3 now is equal to 6 at an angle of 55 times whatever 1 over j6 is in parallel with 10. Same algebra as we did before, so I'll spare you the inner workings, and it turns out to be 1 at an angle of minus 54 degrees. And similarly, that current, same rule, is going to be V sub 3 divided by 10. So it's going to be 0.1 at an angle of minus 54 degrees, not 540. And so together, P3 is going to be equal to 1/2, using our formula up here, 1/2 of 1 from here times 0.1 times cosine of 0. So where am I getting this formula from? I'm getting it from, this is coming from this part of Parseval's theorem. And when you work it out, it's 0.05. And kind of intuitively satisfying, you'd expect that the power of an upper level harmonic would be a lot less than the power of a lower level harmonic in general. And so therefore, we can now answer the entire question, which is that the P average is going to be equal to 40 plus, from our DC component, plus our first harmonic plus our second harmonic. So all told, that gives us 1.25 plus 0.05, which is rounds to 41.3 watts. And that's our answer.